Welcome back to the natural language processing class. So now we are in week 10, and we're deepening our journey in neural representation learning. This week, we talk about structured prediction. So it's unlike classification. We solve problems such as part-of-speech tagging and parsing. So this week, we have two goals. One is to learn how to use neural models to do structured prediction. And the second is to talk about things we haven't had time to address last week, including how to represent out-of-vocabulary words and how to build deeper models for different tasks. We will talk about three main things. So first, about a so-called graph-based model for structured prediction, which is the counterpart for text classification last week. The second part, we will discuss one more paradigm for structured prediction called transition-based learning. Lastly, I will discuss how to integrate the techniques we learned for structured prediction in linear models, such as conditional random fields, with neural representation learning. So first of all, graph-based models. Let's take a recap for structures. So you've seen this picture a few weeks ago. We have a lot of different structured prediction tasks. For sequence labeling, the output is a sequence that has interdependent label-label correlations. For parsing, the output is a tree structure. And we saw in week 1, there is a dependency tree structure which describes word-word relations. And there's a constituent tree structure which describes hierarchical phrase structures. And for neural modeling, we can roughly take a similar neural network architecture as last week, which has three main components. So on the input level, we have word embedding layer, which translates each word into a dense vector. And there is a sequence encoding layer, which extracts dense features, dynamic features, over the input sequence. And then there is the output layer. For classification, we try to condense the sequence representation into a hidden vector. And then we add an output layer on top of this vector in order to do multi-class classification. For structured prediction, the output structure is slightly different. So we need to change the output layer from a multi-class classifier into something else. And that is what we discuss. But whatever we discuss for this section, the outputs are predicted locally. What do I mean by locally? Imagine that we're doing part-of-speech tagging. We learn the local model, which treats the prediction of each part-of-speech tag as a separate task without considering the tag-tag dependencies. We take this strategy for building neural models. So formally, I can describe our input sequence as W1 to Wn, a sequence of words. And then the embedding representation of these words, x1 to xn. The sequence encoder will learn the hidden representations, h1 to hn. And then we make local predictions. To differentiate this model from the transition-based model we will discuss later, we call all these models graph-based models because they predict the output graph structure directly. Let's look at sequence labeling first. We're trying to solve a part of speech tagging task, which maps the word sequence into a label sequence, T1 to Tn. Okay, as I mentioned earlier, so each tag will be predicted separately. So let's first examine the input layer. As we discussed last week, we want to map each word into a dense embedding vector. And we call that an embedding lookup process. But there is something we didn't discuss last week, which is out-of-vocabulary words. Okay. As you can recall, how do we do word embedding? We used an embedding matrix W to multiply a one-hot word representation to get its embedding. And this W has V, the vocabulary size columns, each column recording the embedding vector of a vocabulary word. Where do we get this vocabulary? Okay. If we pre-train the word embeddings, like we discussed 2 weeks ago, okay, this vocabulary will be collected from the large pre-training corpus. But if we train the neural network from scratch, where the embedding table is initialized randomly, each word having a random initial embedding, then this vocabulary will be collected from our task training data. For example, a set of data with a word sequence and part of speech sequence. Okay? No matter in either case, our vocabulary is predefined, okay, before we do the testing. So in this case, our test data can, in theory, contain words that we've never seen in training, causing OOV problems, okay? So imagine we have a very weird name during testing, okay, and which is not seen in the embedding vocabulary. How do we address this issue? All right. So in week 3, we learned a strategy, right? So which is to have a special token, square angle bracket, OOV, a very special token, to represent all of the out-of-vocabulary words. So similarly in here, we have to add a column, right, in this W. Add a bit in this one-hot vector to embed all of these out-of-vocabulary words, okay? So during testing, if we see a very weird name, we know the last bit corresponds to OOV, and we look up for this OOV embedding to represent it. Okay, so all of the unknown words will be mapped into the same embedding. All right. And then, if you carefully think about it, you realize there are 2 issues. The first issue is, how do we train the OOV token embedding? Because our vocabulary is extracted from our training data. So during training, we don't have unseen words, right? So we cannot train this out-of-vocabulary embedding. One solution to it is, during training of our word embeddings, we randomly flip, okay, low-frequency words into this OOV token. Right? For example, if the word Markov or hyperbole exists only once in our embedding training data, okay, so during some SGD batches, we can just randomly flip this Markov word into OOV word with a certain probability. Okay, in that case, we could train these rare word embeddings during embedding training. Okay, so this is the first question. We can solve this question. But the second question is, okay, this is a strategy, but it doesn't really help us guess the meaning of unknown words. Okay? For example, if we have not seen the word internationalization, okay, in our training data, which is a long word. But everyone could guess the meaning of the word because there's international, there's lization, right? We could guess, okay, what it means. How do we guess the meaning? We look at the spelling of the word, okay? But if we use the strategy of chapter 3, every outer vocabulary word has the same embedding. There's no way we can tell whether this embedding is similar to, okay, a known word. We can't differentiate them. Okay, so one solution that we discussed this week is character embeddings. Okay, so we could find a representation of a word by looking at the character sequence inside it. Before we can represent a word using the character sequence, we have to represent each character in a dense embedding. And how do we do that? As I show you in this picture, okay, the character embedding can be derived using a very similar way to word embeddings. In particular, we could have an embedding lookup matrix here. Okay, so this is a embedding matrix, which is basically an assembly of character embeddings, column by column, just like word embeddings, column by column. Right? So if there are 26 characters, maybe more than that, okay, 50 characters, including punctuation and numbers, etc. Or maybe even more than that, okay, 100, including capital letters, lower letters, etc. We could have 100 columns, okay, for this embedding matrix. And each column is a vector of the embedding of a specific character. And then, given a character, we find its one hot representation. We use the embedding matrix to multiply that. We get its embedding. And character embeddings can be randomly initialized and trained during the training of the neural network for part-of-speech tagging. Okay. So now that we solved the mapping between each character and its vector representation, we have to find a way to represent the character sequence. Right? How do we do that? We learned different neural networks last week to turn a sequence of vectors into one, and we can make use of that. For example, we can use a CNN plus pooling, right, to find the character-based representation of the sequence, where CNN can extract n-gram features like lization, zation, or tion, and pooling can assemble these character n-gram representations. All in all, we represent this sequence encoder neural network as encoder, okay, which has its own parameters. And we use CHR of W to represent the encoding result, which is a hidden vector. And then we could concatenate our already learned word embedding with this newly learned character-based word embedding as the new representation of the word xi. Okay? So this is a longer vector. A half of it is the word embedding with a special OOV token. And another half of it is the character sequence encoding, which helps us to guess the meaning of an unknown word. Okay? All right, with that, we can move on to the next layer of our pulse tagger, our part-of-speech tagger. So the sequence encoding layer is nothing new to us, and we can make use of a stacked BioSTM layer or a self-attention neural network layer, okay, to represent this sequence of embeddings. And we get a sequence of hidden states. And each hidden state will represent not only the current word, but also its neighbors, right, in the sequence. And then we are ready to build the output layer. So when we have a hidden representation of each word, we can predict its corresponding part of speech locally. It's unlike hidden Markov models. It's unlike conditional random fields. When we have hi, the hidden vector for the ith word, we just directly connect an output classifier on top of it, okay, to predict its part of speech label. If you write it formally, the output layer on each word is the same. It's a multi-class classifier, right? Using softmax activation. So this is nothing but a neuron we learned in week 5. All right? So, and when we get this p vector, okay, of the text set size, so each element in the p vector will describe the probability of a specific part of speech tag, okay? And we're done. That's the neural network we have, okay? It's very different from hidden Markov model, right? So when we have the word sequence, we first turn them into embeddings, character-based and word-based, and then several layers of bidirectional LSTM, and then each word has its own part of speech, okay? So how do we train it? Because this is a probability model, so we can turn the gold word and part of speech sequences into each individual gold part of speech tag, okay? And then the loss is the standard cross entropy loss over the log probabilities of each tag in each sequence. You see, this data likelihood has two summations, right? The outer summation iterates over all the training instances. Nothing surprising. The second summation iterates through every word location in a particular training instance, right? So we sum up the log probability of each tag separately. So this is a local model, a local graph-based model. All right. And then you know, whenever you have a neural network, you can do its training. The training is SGD and its variants, such as eta, grad, etc., right? But when you train a neural network, you've got to know how to calculate the gradients of each layer. And we already have knowledge on everything. You say, really? Really? You look at every layer. We know the backpropagation rules for every layer, okay? Output is a single neuron. We know it. Sequence encoding is bidirectional LSTM. We calculated it last week. Character-based word embedding, CNN pooling, we know every component. So we can do backpropagation. There is one thing, which is the gradients of your sequence encoding layer now comes from each individual part of speech tag, okay, accumulated together. For classification, we have a single hidden layer. We have a single hidden representation, right, which is connected to the output layer. But for sequence labeling, every hidden representation, HI, is connected to its own output layer. And therefore, the gradient will propagate back to this hidden representation. And then it will propagate to both the history in the forward direction and the history in the backward direction in the bi-LSTM. So basically, the gradient will just mix up from every part of speech tag in the bi-LSTM, okay? You accumulate gradients. And similarly for every input X, right? You have gradients from the forward LSTM component and from the backward LSTM component. You add them together. So in this neural network structure, you will see gradient from here and there. and during the training of an SGD epoch. This is something to mention, okay? But we mentioned the accumulation of gradients to the input vector last week from BioSTM. This is not surprising anymore. But the question I want to ask is, this is a simple feed-forward structure, okay? Without considering the output sequence as a whole. But several weeks ago, when we learned structured prediction for sequence labeling, we learned HMM and CRF, both of which predict the label sequence as a whole. Now, without explicitly modeling tag-tag dependencies, such as adjectives are followed by nouns, verbs are followed by adverbs, can this model work well? So it turns out that this model works very well, okay? Even surpassing the accuracies of conditional random fields. Why is that so? Okay. It's because although we don't explicitly model tag-tag dependencies as a feature, okay, we have a very rich nonlinear representation of the input sequence. All right. When we train the model, as we saw earlier, so there are a lot of losses, right, from every part-of-speech label. They accumulate to the representation of this input, okay? So training over part-of-speech tagging enriches the sequence representation over and over again. Injecting knowledge about tag-tag dependencies into the sequence representation of the input. You can think of, okay, we learned a lot of features about this input sequence that allows us to predict each tag locally correctly by implicitly considering tag-tag dependencies. The representation is so powerful that you have to consider some techniques to avoid overfitting, such as L2 regularization and dropout, which we learned. And a final remark is, although this local model works well, we will see in the third section later, it also combines well with a global model, okay? So this is the power of neural representation. But as I mentioned last week, a drawback is that it's not so interpretable, because in the end, all you get is a set of vectors. You don't quite know what they mean. Okay, now we're ready to embark on more structures. So because the term is short, we didn't have time to talk about linear models for dependency parsing and constituent parsing, or word segmentation. So we'll make up for that this week when we discuss neural models. For dependency parsing, the input is a sequence of word and part-of-speech pairs, okay? Let us assume that every word is assigned a part-of-speech tag before we parse the structure. This is a traditional computational linguistics pipeline, okay? The output is a dependency tree, all right? But how do we represent the tree? If you carefully look into it, you'll find that a tree consists of word-word relations, right? Every word, okay, has exactly one head word, except for the root word of the sentence, which is typically the word, the verb, or the predicate. Right, except for this root word, every other word in the sentence modifies exactly one word. For example, the subject, I, modifies the predicate like, okay? The object code modifies the predicate like. And the pronoun his, okay, modifies the noun code, right? So, and these three arcs forms a dependency tree. If we add a special token, okay, a pseudo root in the beginning of the sentence, then including the root word, okay, every word modifies exactly one word. And this is a tree structure. And also we learned that we can break this tree structure into local structures, which are the word-word dependencies. These are arcs, okay? For each arc, we have three components. So one is the head word, index. The other is the modifier word, index. The third is the dependency label between the head word and modifier word. I denote this triplet as I, HI, and LI, where I means the ith word, because each word needs to have a head word to modify. HI means the index of its head word, and LI means the dependency label. So when we look at the example here, the first word, I equals 1, okay, which is the pronoun I. Its head word has an index 2, so H1 is equal to 2. Okay, it modifies like. And L1 is the subject label in the label set, right? All right, so for dependency parsing, as long as we can predict the set of word-word dependencies, we can build the parser in theory. Okay, and on the right-hand side, I showed you an invalid tree, incorrect tree, which is not a tree structure at all. Okay? So again, let's follow the model structure on the right, okay? And look at the input layer. I want to turn a word and part of speech pair into a dense embedding, okay? And we learn how to represent a word by concatenating the word vector and a character-based word vector, right? And how do we represent a part of speech tag in a dense vector? The same thinking can work. We can have a part of speech embedding lookup table to store the part of speech embedding for each pulse label, okay? And this matrix can be initialized randomly, which means that we give a random value to each part of speech embedding. And then we train the lookup matrix during the training of our dependency parser. And in the end, we will have a value for each part of speech. I guess I don't have to repeat myself with more details. So in the end, the xi, or the representation of the ith word, will be the embedding of the word concatenated with the character-based representation of the word, concatenated with the embedding of the part of speech, okay? So now that we've learned the embedding of characters and part of speech labels, we know that we can embed everything. If this everything is a closed set of labels, right? You can use the same technique to embed everything. This is the input layer. For the sequence encoding layer, I really don't have too much to say. Because again, we can use bidirectional LSTM to calculate a hidden state for every input token. And we can stack multiple layers of BioSTM. And now we are at the output layer, okay, which must be different from the classifier and sequence labeler. Because now we're talking about predicting a set of labels how do we do that? Okay. So maybe let me draw it. So first of all, we need to find a label or a head word for each input word. Okay. So we need to calculate the correlation between every two words in the sequence. And to this end, okay, we can take the hidden hi and hj. All right. I'm using this as a vector. I'm using this as a vector as well. Okay. I take two embedding vectors. Okay, not embedding vectors, hidden representation vectors. I can concatenate them together, all right, into a longer vector. And I can pass that through a neural network layer to calculate a single score. I can do that, right? And how do I pass it through a single neural layer? You know, we can use V transpose hi concatenated with hj. So this is one layer, one neural layer, right? And that calculates a score. So when I have a word hi, I want to find its head, right? So I can calculate a score, Sij, between this hi and every j not equal to I, right? And I select the one that has the highest Sij. I found its head, right? Okay. So given every word, I look at the correlation between every other word, and we select the one that has the highest score as its head. Okay, so this is the problem setting. And in order to calculate Sij, I said I can use a single neural network to do that. All right? But we could do something more complicated, as I show you in this slide. So in addition to a single neural network, okay, I add another hi, u, hj. This is another term in the score calculation. And this is actually a tensor product, right? I think we saw a tensor product somewhere. Where? In the log bilinear model for training word embeddings, right? So again, you see that again. I put it here. Why do I put the tensor here? Because I want every element in hi to interact with every element in hj. You know, this simple concatenation doesn't quite do that. And we add this, okay, to enrich the representation. But you say, okay, so this is only one way to calculate the score. I can improve over that through another method. I can use a multi-layer perceptron over hi plus hj. I can also calculate a score, right? And that also enriches the interaction between hi and hj. That's possible. I take this because this is a famous paper in the field of dependency parsing, all right? And by this, you also learn the flexibility of defining your neural calculators. The remaining of these equations are just like what I described, okay? Every word find its head word. But that's not the end. You want every word to find its head, but you also want a dependency arc label, right, over each dependency arc. That can be done similarly, right? Because when you have the dependency arc, you already know hi and hj, or hi and hi, right? So we can use these two hidden vectors as a basis for predicting the dependency arc. And that's nothing but a multi-class classification problem, right? The only difference between part-of-speech tagging is now that we have two words and a dependency arc label. Part-of-speech tagging is one word and a pause label. Right? So we can use a single multi-class classifier neuron on top of HI concatenated with HJ to do the label prediction. But this parser extends over that. So in addition to a single neuron, they also added this tensor scoring function. Okay. So when we have the tensor plus a standard feed-forward layer plus a bias vector B prime, okay, we get a score vector where each element in the vector is the score of a particular label. And then we use a softmax activation over this scoring vector to get the arc probability, arc label probability. That's the dependency parser, okay? A quick recap. Given a word and tag sequence, we first turn every word tag pair into a dense vector xi, all right? And then we put a sequence encoder to get hi over every word tag pair. And then we do two things. One is for each hi, we find the head, okay, by calculating a score between hi and every hj. That finds an unlabeled tree structure. And then, given every label in the unlabeled tree structure, we do a multi-class classification. The only difference between this classifier and the standard multi-class classifier is that the score has one more component, which is the bi-affine component. As a result, this parser is called the bi-affine parser. Okay? This parser was proposed by Stanford University. For training, you have a set of sentences with gold standard dependency trees, manually labeled dependency trees. We call such a corpus a tree bank in computational linguistics. When you have a tree bank, you just break the trees into individual word-word dependency labels, okay, dependency arcs, and each individual arc label. And we can have a cross-entropy loss over both the structure and the labels, as you see in this slide. Okay? All right. So the dependency parser is different from the part-of-speech tagger only in the output layer. All right. So similar backpropagation training will happen, and the gradients will flow from every dependency label to the hidden layers and backpropagated to the sequence encoders and the part-of-speech embeddings and the character embeddings and the character-based word representation layers and the word embeddings. Okay, so every neuron will be trained. There's one thing we didn't discuss, though. We discussed the scoring, and we discussed the prediction of every dependency arc, right? It's completely possible that according to the scores, we get a structure with loops, okay? You know a graph, you learn in graph classes in mathematics that a graph with n vertices and n minus 1 edges is not necessarily a tree, right? A tree is a fully connected graph with n vertices and n minus 1 edges. But we can end up with something with inner loops and separations, so which is not a tree. So how do you solve the problem? You need to make use of your knowledge in the algorithm class, okay? I want to find a tree, okay? I want to add up all these arc scores to find a highest scored tree with the total arc score, the sum of the arc score being the largest. What is this? What is this algorithm called? Maximum spanning tree, okay? Yes, a lot of you are familiar with that. So I need a, okay, is it a greedy algorithm? Is it a dynamic program? Depends on whether you have arc dependency features, right? Do you have that? You don't have that. Every arc is predicted separately. So you have a greedy maximum spanning tree algorithm. You can name a few, right? Okay. To do this is called decoding. Do you remember the Viterbi algorithm we learned for HMM? Okay. So dependency trees also have the decoding problem. Unfortunately, because the term is short, I don't have time to go into details, but I guess you already learned maximum spanning tree algorithms. So let's move on to constituent parsing. Okay, this is again a structure. It's not a single class label, but when you have an input sequence of word and part of speech pairs, you want to predict a hierarchical phrase tree, hierarchical phrase structure tree. So this is a tree with, okay, embedded noun phrases, verb phrases, and sentence structures, one over another, okay? My first question is, how do you separate this tree into independent substructures? Okay? So this is the first question. And the way, one way of doing it is to split the tree into subtrees or spans. Just as I show you in this example, there's a noun phrase, his coat, right? There's a verb phrase, like his coat, that contains the noun phrase. There's a sentence, I like his coat, that contains the verb phrase. And every phrase structure can be represented as a labeled span. His coat, okay, is a span over the third to the fourth word with the constituent label noun phrase. So I can use 3, 4, and NP to represent the span, where 3 is the beginning index, 4 is the ending index, and NP is the label. So similarly, we have 2, 4, VP, right? And we have 1, 4, S. And this way, we're able to break a hierarchical tree into individual spans. And the goal is to predict the set of spans, B, E, and C, beginning, ending, and constituent label, okay? Oh, and immediately you realize that this is something about 2 words, right? As soon as we can get the beginning word, the end word representation, we can sort of make use of them to predict the span label, or whether there is a span. Okay, so let's look at it, okay? So we want to enumerate all possible spans over the sequence. How many are they? It's quadratic asymptotically, right? Okay, 1, 1, 1, 2, 1, 3, 2, 2, 2, 3, 3, 3, etc., right? So many spans. And how do we model whether there is a constituent label over the span or not? We can unify, okay, the labels and whether it's a constituent or not. And in particular, we use C to denote the label set, the noun phrase, the verb phrase, the adjective phrase, etc., right? And we use phi to denote the fact that this is not a constituent span. So your total label set will be the constituent label set union phi, okay? And the modeling target is to predict this C hat given the sentence context, the beginning index, and the end index. I give you two examples on the right. So when you're given I like his, 1, 2, 3, the span, I must predict phi because it's not a constituent. But if I give it 2 to 4, you know this is a verb phrase, so you predict its label. All right? So when we build this modeling target, we unify the prediction of constituent span and the label. Now, about parameterization. We can take, again, the old structure. We have the input layer, sequence encoding layer, and the output layer. And I don't need to say again that the input layer can be exactly the same as our dependency parser, and the sequence encoding layer can be the same, like stacked by LSTMs. All right? And now, we need to represent every span. Okay? There are different ways to represent a span. So, you know, what we have is a sequence of hidden, and a span can be from a beginning index B to an ending index E. Okay? For example, 2 to 4, all right? And there are many, many, many hidden representations in this span, if the span is above size 2, okay? Now, how do you represent the span? So one way is to take pooling, maybe. Can I just use some pooling, okay, over all this? Yes, I can, right? Another way is to use attention. Can I? I get a separate query vector, which is a model parameter. I use the query vector to do a weighted sum between these, okay, or hidden representations. I can also get a hidden vector. I call it maybe the hidden representation of the span, okay? But here, in this class, we used a very simple way. I just concatenated HB and HE. Can that represent the whole span? Of course, the answer is yes, but why is that so? It's because HB already contains information of the whole sequence. I'm using a bi-LSTM. And HE contains information over the whole sequence. When we concatenate the two, it only tells my model, okay, this is the range of the span. And that's all. And when we learn the constituent parsing task, okay, gradient will backpropagate to this side and to that side to help us, okay, adjust the dynamic representations of all these hiddens so that the concatenation of the two indicates the span information. All right. That can appear amazing or counterintuitive to you in the beginning, but remember, the representation is so powerful, okay, that you can inject any kind of knowledge inside it. All right, so let's just use S, BE for the span embedding, and there is a ON squared number of spans. For each span, we need to do a prediction, and this time, let's do the boring thing. We add a standard multi-layer classifier on top of the S, right? You can see that the first layer is a 10H activated neuron. The second layer is a softmax activated neuron, okay? So it's an MLP over the concatenation of HB and HE. All right, and that predicts the probability of our modeling target. All right. Okay, so given these probabilities, how do we build a tree? How do we build a tree? We have to build valid trees. If for every span we just select the highest scored case, it's not a valid tree. It's not necessarily a valid tree, right? We could have overlapping spans or some weird structures which is not hierarchical. How do we ensure that it's hierarchical? Okay, so our search space, it's not the space of all possible span concatenations, okay? This is the search space of all possible span concatenations. Inside it, there's a subspan of all valid trees, okay? We need to search for the highest scored valid tree, all right? How do we do that? Okay, we can first predict the unstructured tree, unlabeled tree, sorry. And we can do that by summing up the score of all constituent labels into py equals 1, okay? Py equals 1 means that this is a constituent, okay? And we can use phi as py equals 0. This is not a constituent, all right? And we want to find a tree that has the highest sum of these two scores as an unlabeled constituent tree. How do you do that? This is not a maximum spanning tree algorithm, but some of you might have learned it. I'm not sure here because you don't learn the compiler course, right? But this is called Kasami CKY. I only remember Kasami and Younger. I forgot the other name. Okay, anyway, so this is the surnames of 3 people who independently found this dynamic program algorithm, okay? And we can use the dynamic program to find the highest scored constituent tree, okay? All right. If you're interested in the algorithm, please look at chapter 10 in the first edition, which will be chapter 11 in the second edition of my textbook. There are a lot of details, okay, which I don't have time to explain. All right, after you found the unlabeled tree, you can predict a label on each span. Training will be similar, okay? Given a tree bank, and this time for English constituent tree, the tree bank, the famous tree bank name is Pan Tree Bank, okay? You can take a look. It's a very famous tree bank. For Chinese, you have a corpus called Chinese Tree Bank, okay? If you're interested in computational linguistics, you can study that. And anyway, so given a set of sentences with gold trees, you can break these trees into individual spans and you minimize the cross-entropy loss. So now, let's discuss a second paradigm for structured prediction. You know, we've learned the local models earlier. So if you're interested in other structured prediction tasks, such as relation extraction, right, or event extraction, you can build your models similar to those models. But here, I want to take the chance of another modeling paradigm to illustrate how do you learn representations using neural network, okay? So this is a very different way of doing structured prediction. It's called transition-based models. This kind of models don't directly predict the graph structure, but turns instead the output building process into a state transition process, where each state represents a partially built output, and transition actions are used, okay, to consume inputs and build output incrementally. Let me take dependency parsing as an example to illustrate transition-based structured prediction. So we have a state which represents a partially built parse tree, okay? And this state consists of a stack. I denote it with sigma. A buffer, I denote it with beta, okay? And a set of arcs that are already built, okay? For example, if I have a sentence, he gave her a pen, okay? During the parsing process, you might have a state like this, you know. The stack contains some words and partially built trees. The buffer contains the remaining words, okay? And you use actions to consume words from the buffer and then build the tree on the stack. And these actions are listed here. They include shift, left arc, right arc, and reduce, okay? Now how does it work? Let me show you a small animation, okay? So, all right, this set of actions are called the arc standard parser, all right? So initially, the stack is empty and the buffer contains the whole sentence, all right? And then we need to keep on applying transition actions to build the parse tree. The first action is called shift, which moves the front of the buffer onto the stack. You see, the word he is on the stack, right? The next action is shift, which moves the next word give onto the stack, okay? Now you have two things on top of the stack. You can apply some arc actions. So this time, I have left arc subject. What does it mean? It takes the top two items on the stack, okay, and build a left arc between them, okay, pointing from the second word to the first word. Actually, pointing from the top of the stack to the second top of the stack, right? Left arc. The arc is subject, okay? And we'll build this arc, you know, you already found a head word for the first word, he is the subject. So you pop he off the stack, okay? So this is left arc. And then I continue to shift her onto the stack. Okay, now the next action to take, okay, again, applies to the top two items on the stack, okay? The top of the stack is her, the second top of the stack is gave, okay? And now we need to build a right arc to make her the object of give, okay? And similarly, because her has already found the head word, I pop it. And next is to shift the word onto the stack. And then I shift the word pen onto the stack. Guess what happens next? You need to build a left arc, right? Because modifies pen, left arc. Again, it happens to the top two items on the stack. And then what do? You build a right arc to make pen an indirect object of give. And then you're done. The end, okay? So you got a tree. You see, this process is different from graph-based parsing in the sense that I translated the graph structure into a set of actions. And so this is basically a decision process, right? State transition process. I start with S0, which corresponds to an empty structure, all right? And I apply one action after another until Sn, the final state, okay? It turns out that for arc standard dependency parser, you need 2n-1 actions to finish parsing. Okay? You know, each action is ambiguous, right? So every time you can take 4 types of actions. And if you consider the dependency labels, it's much more than 4. Okay, tens of different actions. So this is a search tree. You know, S0 is here. For S1, you can have multiple choices. For S2, given every S1, you have multiple choices. So this is a growing search space. And basically, the goal of a transition-based model is to find a path, you know, over this search space, which is drawn here. So we want to build a neural model to this end. Of course, this is a good exercise for our techniques. The key issue is, how do you find a neural representation of a state so that you can do the next action prediction? Okay, so this is the question. And we want to use 3 different models. Okay, these 3 models are real. They are academic papers. But they are very nice examples to show you, okay, the thinking of deepening neural thinking. Okay. So the first model is actually from Stanford. It's basically can be understood as a neural version of my linear model. I don't have time to introduce my linear model, but it's written in chapter 11 of the textbook. Okay. How do you represent a state so that you can score the next action? That's the question. And you know, a state can be represented by the top words on the stack and the front words in the buffer. They are the most representative. Okay. For example, I can use S0 to represent the front word on the stack, S1 to represent the next front word, so. And B0 to represent the front word on the buffer, B1 to represent the next word in the buffer. Okay? If we can sort of combine this information, for example, if I know, okay, the top of stack is her, okay? Second top of stack is gave. And then the buffer, front of buffer is the next in the buffer is pen. If we're in such a state, okay, what action should we take? All right? So maybe the clever model will learn that if her, gave, and her are on the stack, okay, the next words are a pen, we'd better make her an object of gave. Okay? So we need to tell the model who are on the stack, who are in the buffer. Okay? And how do we tell the model? This is the model structure. Okay? So in the bottom are the input sequence, word and part of speech. And each of them are represented using an embedding, the embedding of a word, the embedding of a part of speech, etc. And then you know, in this input sequence, some of them are on the stack, okay? And some of them are on the buffer. I just use S0, S1, etc. to represent them. So our idea is we can extract the word and part of speech representation of the front items on the stack and the buffer, okay? And also the dependency arc labels over the arcs we've already built. We integrate them together as the input representation, okay? Specifically, we extract 18 different locations on the stack, okay, including S0, S1, and maybe the left modifier for S0 right modifier of S1, etc. There are 18 of them. So I represent each of these 18 things with their word embeddings and part of speech embeddings. That's possible, right? And then for things that we already built on the stack, such as he is the subject of gave, okay? We can extract 12 label features, dependency arc label features. They are at different locations, okay? So we got 18 word embeddings, 18 part of speech embeddings, and 12 dependency arc label embeddings. Oh, you say, you didn't teach me how to do dependency arc label embedding, but I assume every one of you can do that already, okay? Just like characters and tags. So I concatenate them together. I concatenate 18 and 18 and 12 into a large vector, okay? And then what I do, I use a single neuron to induce a hidden representation of these things. And then I use a multi-class classifier on top of this hidden representation for predicting the next action. Okay? And that's it. That's model 1. How do I train it? When I have a dependency tree, I can devise an algorithm to translate the tree into a state transition sequence. Okay? And then I can break the sequence into a sequence of state input and action output. I can minimize the negative log likelihood of this data set for training. That's the first model, okay? Model 2. The first model basically puts a lot of features together, you know? Each feature is an embedding. It's very much like manually defining features. Okay? It didn't quite get the sequence information. You know, for the graph-based models, we had a sequence encoder, right? And then we extract features. They're more global. And now we're just combining the stack information, buffer information locally. So the top of the stack doesn't really tell me, okay, the beginning of a sentence is he, for example. Can we find, okay, representations of the stack and buffer features that contains context? That's model 2. Model 2 is this structure. So in the bottom, again, it's a word and part of speech sequence. But different from model 1, we don't just concatenate their embeddings together, but we first feed that to a bidirectional LSTM. Okay? So the representation of every word knows not only the current word, but also the whole sentence. Okay? And this time I say, the top of the stack is her. But it's her in he gave her a pen. Okay? So this gives us much more information. Because of that, okay, model 2 will just consist of the following layers. The input layer, okay, translates word and tag pairs into embeddings. The sequence encoding layer finds a hidden representation for each input. And then the stack and buffer features will be easier. We don't have to take the top of stack, the second top of stack, the third top of stack anymore. But we just need to take the front 3 items of the stack and front 1 item from the buffer, only 4 items, rather than 18, okay? Why 4 will be enough? Because each of the 4 already tells us information over the global sentence. So 4 will be sufficient. Okay? We concatenate, okay, the hidden representations of the 4 into one hidden vector, and then we pass that through a multi-layer classifier. That's our model 2. Training of this model is exactly the same as training for model 1. Okay. Now let's move on to model 3. Can we take even one step further? If you look at model 2, you say, okay, the advantage is I use the sentential information for representing age. And I use the top of stack, use the top 3 items on the stack. Wait, these 3 items, they tell us information over the sentence, but they don't tell us information about the stack, right? Maybe the stack contains 10 items. I only know the top 3. Can we have information about all these 10? That's my question, okay? So similarly, I only use a feature which is the front of the buffer. Of course, it tells us the whole sequence, and buffer is the remaining of the sentence. But we don't explicitly represent the buffer. Okay? Can we take items on the stack as another sequence, items on the buffer as another sequence, and I use a sequence encoder to represent them? That's my question, right? That leads to model 3, okay? All right, it's more complicated than model 2, which, okay, you see the bottom layers are the same. There's a bi-LSTM sequence encoder. But on top of the bi-LSTM sequence encoder, there's a stack sequence encoder. There's a buffer sequence encoder. There's an action sequence encoder. What is the action sequence encoder? It encodes whatever action sequences were already taken, okay, as a history. So if already shifted, left arced, what's the probability of a right arc? Okay, so this is what the action sequence encoder does. All right, so how to encode these sequences? You say, I can use LSTM to do that, right? But wait. If given every state, I use a separate LSTM to encode the state, it'll be super slow. Because you know, you need 2n-1 actions to finish parsing. If every state is represented from scratch, the parser will be slow. I want to be incrementally modify my sequence representation, okay? So that I don't have to use a sequence encoder from scratch. Can we do that? So during the parsing process, can we dynamically change the stack and buffer and action sequence representation? That's the question. It turns out that all of them are feasible. For the buffer, careful observation shows that you only take things off the buffer. You don't add things to the buffer. Okay, you only do shift from the buffer. So to represent the whole buffer information, you only need a right to left LSTM. So that every word, okay, contains information about all the words after it. Okay? So every time you shift a word onto the stack, your buffer front moves one step on the right. Okay? So you can encode the whole buffer by using one right to left LSTM on top of the bi-LSTM sequence encoder. Okay? So you can incrementally change the buffer front pointer, okay, when you shift things off the buffer. That's the buffer. How about action history? action history can be dealt with similarly. So you can use one left to right LSTM to represent the whole actions history. Because actions, you only add to them, you don't delete from them. So whenever you take a new action, you add one LSTM step to the action history. And that can be incrementally calculated. Okay. Now you say, how do you turn actions into embeddings? Okay, I don't have to repeat myself. Okay, it's similar to tag embeddings. But the most challenging thing is the stack, you know? Because the stack, sometimes you push things onto the stack. Sometimes you pop things off the stack. Can a stack be incrementally represented? So we need to examine the pushing and popping actions more carefully, okay? So when you push things onto the stack, it's like an action history LSTM, you know? When you push a new word onto the stack, you just add its hidden representation to the stack LSTM sequence. It's like action LSTM. When you pop things off the stack, it's a little bit like the buffer LSTM, you know? You just need to change the pointer of the stack front one word to the left. Right, so the popped word does not affect the stack representation anymore. What if you push something else onto the stack after you pop? Okay? So this is the only tricky thing, right? You want a new sequence on the stack where the old front of the stack was popped and a new front of stack is added. Okay. It turns out that this doesn't really matter. For example, if you pop things off the stack, so this thing will no longer be needed, right? The stack top is here. You only need to start from here and add another LSTM stack with a new input, ending up with the picture below, okay? So your stack representation branched, you know. The old branch is no longer used. The new branch is calculated incrementally. Okay, again, this doesn't take O(n) time, but just take O1 time. Right. Okay, so given what I just described, Model 3 make things easy, okay? So the input layer is word and part of speech representation. The sequence encoding layer is stacked LSTM. And then when you have a stack, when you have a buffer, when you have an actions history, you use 3 dynamically adjusted LSTM to represent each, okay? And you can use the last hidden state from the 3 LSTMs to represent the 3 sequences. HS to represent the stack, as I showed you earlier. HS points to the last state in the LSTM, stack LSTM. So HB is the front of the buffer to represent the whole buffer. And HA is the end of the action history buffer to represent the whole history. And you can use the 3 to represent the 3 components. You concatenate them together and pass it to a multi-class classifier. You can predict the action, okay? All right, and the 3 incremental models showed us the power of neural network, okay, for building transition-based models. Lastly, all the models we learned by now are local models, okay? Especially the graph-based models, we predicted each substructure individually. The transition-based model is also local model because we made decisions locally, you know. It's a greedy algorithm, right? One action, second action, third action. We don't consider the ambiguities. In the end, we want to find the highest scored action sequence. But the locally optimum action might not be in the optimum sequence. Okay? So for both graph-based models and transition-based models, we have a local modeling and global modeling issue. Transition-based global model, I don't have time in class to discuss it. But if you're interested, you read the textbook. Okay? Now we talk about graph-based global model. You have to remember conditional random field again. What is it? It takes the whole output sequence as the modeling target, you know. And we learned CRF for sequence labeling. We did not learn tree CRF, okay? If you're interested in the tree CRF, read chapter 10, okay? So this is an equation you already learned. Given a word and tag sequence pair, I use phi, okay, a manually defined feature vector to represent the pair. And I use theta dot phi to score the pair. And I use softmax for activation. This is my CRF. To allow efficient decoding, we broke this global representation into the sum of local representations, okay? Where the local features are the same as maximum entropy Markov model. The features are local, right? It could be first order, second order, etc. So here I just use the first order case, for example. All right, so this is CRF. You all remembered it. My question is, how do you build a neural version of this model? Okay. To build a neural CRF, all you need to do is to replace this theta dot phi scoring with a neural network. All right? And we will see several strategies to achieve it. First one, I put the linear CRF on the box, okay? And I say, I want to replace this theta dot phi notation, okay, with a neural network. And to this end, okay, I still keep this summation sign, okay? It's still the sum of local features. But I want each local feature to consist of two tags, two part-of-speech tags, and a 5-word window. This is a very simple version of neural CRF, okay? The original CRF, when we defined the feature vector phi, we roughly did the same, you know, 5 words and 2 tags, okay? Now we just change, we just replace, okay, theta dot phi to a neural scoring. To that end, let's first concatenate the word embedding of the 5-word window into a long vector, okay, to represent the words. Can I? And I name it X. X is a big vector, okay? And then from the 5-word representation, I want to calculate the word and tag pair score, okay? I first map this 5-word embedding concatenation into a hidden representation of the 5 words by adding a TAN-H activated neural layer, as I show you in this equation. This is also easy to understand, right? Now we extract it. So this is a CNN, a convolutional layer, right? You can imagine. So it extracts 5 gram information. And then given this 5 gram feature H, how do I calculate the word tag combined score? And in this equation, I just respected the original NeuroCRF paper, okay? I use U times H to calculate a score where this U, okay, is specific to the current tag TI. All right, I use U bracket TI to represent a scoring matrix for TI. Okay, so you can imagine if there are 34 tags, there will be 34 different U's, okay? Each U for each tag. And then I add this U times H to a B TI, TI minus 1. What is that? Okay, that is a single scalar. But this scalar is specific to 2 tag compositions, okay? In other words, there are 34 times 34 B values, okay? Given each tag bigram, we can find a B value, a score for this tag bigram, okay? So U times H is one score, and B is another score. U times H captures word tag interaction, 5-word window and the tag, the interaction. B captures tag-tag transition, okay? So emission and transition, 2 scores added together to replace theta dot phi. Okay? And that is the neural version of the CRF. And you said, oh, this consists of a lot of lookup actions, right? For example, the tag-tag transition is just a lookup over a tag bigram. It's not so clever. Can I do something more clever? Well, you can be flexible, right? So when you have this word representation H, okay, you can do it another way. You do a tag embedding, for example, of TI, all right? And you concatenate this tag embedding with a word representation. You pass that through an NLP. You can also calculate a score, all right? For tag bigrams, you can do the same. You concatenate the embeddings of 2 tags, and you pass it through an NLP. You can also calculate a score. So you are free to define a neural network. So this is a neural CRF, very simple neural CRF, okay? But how do I train it? Okay, so the training, let's use the original parameterization. Consists of the minimization of cross-entropy loss. So this is the same as the original CRF. I just take the negative log probabilities of the training data, and I want to minimize them, okay? So to that end, I need to use SGD, okay? And I need to find the gradients of this loss over every model parameter, okay? But if you carefully look at the CRF formulation, only H, U, and B are in the CRF equation. But you say H is calculated from X, the word embeddings. Don't worry. If we take the CRF as a neural network layer, we can apply the thinking of backpropagation, right? So in this neural layer, who are parameters? U and B, okay, are parameters. Who is the input vector? H, okay? So according to backpropagation rule, we need to find the gradient of the loss over U and B for my own need. And I need to find the gradient over H for the previous layers, all right? The word embeddings and the tan H layer. How do we do that? Let me first take the gradients of the loss over U and B, and let's do it over U. This turns out to be a gradient calculation process that is very similar to our log linear classifier and to our CRF model, okay? It's a feature vector minus the expectation of feature vectors over all possible outputs. As you can see, okay, the gradient is H, okay, the feature vector, minus the expectation over all possible text sequences, the feature vector over that text sequence, okay? And the second expectation can be also the expectation over the local structure, right, which is computationally feasible. I don't have time to go into the details of this computation, but it turns out it's very similar to CRF training. And the gradient over B can be calculated similarly. As I mentioned to you earlier, we need to backpropagate the gradient to H. And it turns out that the U and H are symmetric, okay? The gradient over U contains H, and the gradient over H contains U. It's again U of the gold standard answer, okay, minus the expectation of U over all text sequences. All right. And after you calculated the gradient over H, the backpropagation to other neural layers are simple. So can we do something else to neural CRF? It turns out that we can replace the neural network structure earlier into a more complicated structure. For example, earlier we only extracted features from a 5-word window. Can we extract feature from the whole sequence? Yes, we can use a bio-STM to represent the whole sequence, right? And then when we try to replace, the tag bigram and word 5-gram feature in CRF, we just use H for the current word. And we build a neural scorer, okay, to integrate this H with the tag bigram. And this time I just use H to replace the hidden of the 5-word window MLP, okay, in the neural CRF. And so that the gradient backpropagations are exactly the same as what I described earlier. But of course, you can think about alternative neural architectures, such as, I don't use the lookup table, right, for the model parameters. I just concatenate tag embeddings and word embeddings and feed that to a bi-affine model, feed that to a feed-forward neural network. I can do all this kind of neural designs. That's it. Okay, let me make a summary. For this week, we learned how to do graph-based structured predictors, how to do transition-based structured predictors. We learned how to represent out-of-vocabulary words. And we've learned how to embed everything, right? And finally, we have learned, using a lot of cases, how to make use of neural representation layers to enrich the model. Okay? We'll see you